Hey, so this video is going to be about linear motion and defining motion. And I don't know, the easiest thing, let's just jump in. Linear motion. All right, motion. So, if we're looking at motion, that means we have to be looking at an object. We just need something that represents, well, something that's in motion. If we think of motion, it's like that's like movement, right? So, I don't know, we've got an object. And, here's the ground. Oh, wow, that's pretty uneven ground. Hey, that's a lot better. All right, that'll work. It's mostly straight. Pretend that's an absolutely straight line, okay? So, wow. All right, let's try this one more time. We're going with that one because I don't feel like doing this again. Okay, so we've got, and forget all these dips and stuff, pretend it's a straight line. All right. So, this object is here. For this thing to go in motion, then there has to be some sort of force that is applied in this particular direction right here. All right, easy enough. So when that happens, if you think about it, then that means this thing would move forward from where it started to right here. Let's just freeze time. Let's just pretend that right now it's still in motion, but we've frozen time. If you think about it, then if we think about what we know from our math class, here's our x and here's our y coordinate planes, right? So this thing right here has moved center mass to center mass. It has moved right here along some distance along the x. All right? Some distance along this horizontal plane, whatever it is. So now, unfreeze time, this thing would obviously still be moving. Freeze time, it's right here. Pretend it's the same thing. Well, here's another distance that is traveled. It's still along the same coordinate plane. It's still a value of x, but they're different. So this must be the first distance traveled. This must be the second distance traveled according to the way we are looking at the movement of this, with me freezing time, etc., etc., etc. Unfreeze time, and it moves along. Freeze time again. And you should see that we could define this as x to x sub 3, right? x3. And now, so if we think about this, all right, right here center mass, let's come down. Right here center mass. Right here, center mass has come down. There's been a total change in distance. Remember, the delta symbol means change. And for us, this distance was along the x-axis. All right? And so all of this from here to here, this right here represents the total. Whereas, and the total is obviously x1 plus x2 plus x3, right? That's easy enough. Now, there is a total amount of time that was measured, and so delta t, and obviously we could measure delta t from here to here, from here to here, and then from here to here. And you know in real life that, let's just say this round object here, let's say it represents you. And there's a force applied to you. I mean, in other words, somebody comes up and pushes you. Well, you're going to move in this direction, but you know you don't keep moving at the same speed, right? You don't keep moving as fast. Eventually you slow down. And of course, you know that means probably friction and that type of stuff. So you can think that there's a speed from here to here that is changing. So there's a certain amount of time that's happening here. There's a certain amount of time that's happening here. A certain amount of time that's happening here. So if you think about it, you could calculate the velocity from here, from this point to this point, from this point to this point to that point, and then all of them together would equal basically the average speed in that direction, right? This is basically how we're defining our linear motion along the x-axis. Well, the same thing is going to be true if you were to drop the object. So the object is up here, right? And so here's the ground, right? So this thing is dropped, and then all of a sudden, freeze time, bam, it's right there. Well, it went some distance along the y in this direction, center mass. Unfreeze time, thing goes down, freeze time, obviously it moved again along the y-axis, unfreeze time. All right, and I didn't draw these to scale. It's just a basic concept. Well, if you think about it, we go from all the way at the top to all the way at the bottom. There was a change in distance that was along the y-axis. Okay, and we know that gravity basically pulled this down, and we're going to look at that in a whole lot more detail in other lessons later on in the semester. So that's basically it. So what we did was we defined motion as basically the movement of an object along what we know is an axis. And right now it means either that's going to mean either two. We say this is its starting point. It's going to be in either direction along a horizontal axis, or it's going to be along a vertical axis. All right, and so this representing x, this representing y, and so in this direction tends to be positive. Up direction is also positive. When we think in this direction, we tend to think negative. When we think in this direction, we tend to think a negative value as well. And so all we're doing is bringing in all those skill sets that our algebra teachers taught us, and then we're just going to apply it to some basic things in physics and then some more complicated things in physics. All right. Now let's take a look at the difference between distance and displacement. And so there are times when they both are the same thing, but oftentimes they are not. So let's think about this. When we talk about distance, and we do represent distance with a lowercase d, okay? And we tend to represent displacement with where it is along the axis. So that means we would obviously use x or we would use y. And then you're going to find that when we look at various physics equations that you'll just see the letter D there, and there's some assumptions you have to make that, oh, this was a displacement, and it's vertical, so you know that you're really substituting for y, or if it's horizontal, you're really substituting for x. And depending on which physics textbook you look at, some people very religiously use x or y, and then others just use d for lowercase d for everything. So I'm just trying to get you familiar with some of the different language that you're going to be coming into contact with. Okay, so when we look at something of this nature, let's think about this for just a second. If an object starts here and then it moves in this direction and stops right there, then we can say without beyond a shadow of doubt that all of this right here is the distance that it has traveled. This is the change in its distance. Now let's just say that you move like this to get to that point right there. Pretty colors, huh? So let's think about this for a second. You started here and you finished here. Question is what's your distance And the other question is what is your displacement? Okay. So the distance, let's just say that from here to here represents let's just say this represents 10 meters. I'm just making this up. The distance in our very first example, before I actually drew this nice galaxy looking line, right? When I first did this and we went from here to here, our distance equals 10 meters. Now, when I do something like this, distance is greater than 10 meters. And the reason for that is because you literally are traveling this path here, going all of this. That's a different amount of actual, your body is, or the object is, whatever, is literally moving along a different path. So obviously your distance is greater than 10 meters, but your displacement, which in this case is a vertical displacement, we would say delta y equals 10 meters. Because we already had assigned this distance here 10 meters. So this is where you started. This was your starting point. This was your stopping or end point. So distance is literally a measurement of how much you actually travel, how much an object actually is when it's in motion, the measurement of how much it actually moves. Displacement is where did the object start and where did the object stop when it's no longer in motion. So in this example down here, even though the starting point and the stopping point are in the same place, the distance traveled is greater than 10 meters because it's going to take a whole lot more than 10 meters to go this walking path through the woods. But if you just walk straight from here to here, first you're in this place, now you're in this place, you still have the same displacement even though you took this larger path. So if I were to come up here, erase this, okay? If I were to erase this and I were to ask from this picture here, what is your distance? You would tell me 10 meters. What is your displacement? You would also tell me 10 meters because you literally traveled the same path each time. First you're in this place. This is where you started. This is where you ended up. In this second example here, you start here. What's your distance traveled? Well, obviously, this is a whole lot more than 10 meters, so I wrote distance equals greater than 10 meters. But you still started here, ended up here, so your displacement equals 10 meters. So keep in mind that a simple definition for displacement is the straight line measurement between the starting and the stopping point. It is literally a straight line, a distance from the start to the end points. Okay, that's pretty much what displacement is. It may take more distance. So, for instance, you pull. You're in a classroom, and you walk from one classroom to the other a straight line distance. Your displacement is still the same. The second time you walk out of the classroom, you walk downstairs, you go to the front office, and then you walk to the gym, then you go to the restroom, and then you go to the other end of the hall, and then you finally make it to the class you're supposed to. Well, you traveled a much greater distance, but you're finally in the same place. Your displacement would be the same. Your final displacement would be the same. Okay? So I hope that clears that up. It's really not that difficult of a topic. Um, so there's one other thing that I would like to talk about as far as this goes. So let me sort of draw this off to the side and use this right here, and that will be the difference between a scalar versus a vector quantity. Okay, so let's do this. I'll just duplicate the slide. No need to um, no need to make it so. Alright, fine. Here we go. I'm just cleaning this up for you a little bit. Blah, 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 blah. Okay, I guess I could have just made a blank slide for you. Alright. But just bear with me for a second. I just wanted some more real estate. I just thought about this. I was going to make a separate video, but you know what? Since we're here, let's just do it all in one video. This is very informal. It's just like teaching. Things don't have to, this is not, I'm not trying to win an Oscar performance here or whatever. You just need the lesson. Alright, so let's think about this for a second. Alright, forget about, so when we're talking about distance and displacement, it doesn't make a difference. So what I do want to talk about is the concept of a scalar quantity versus a vector quantity. Okay, so let's think about this. We can go back to what you learned, basic algebra. Scalar quantity, we would be talking about the concept of just speed. How fast is the object moving, right? And so we would say the object is moving along this linear path, or it's moving along this linear path here, right? And so we've got, you know, velocity equals a change in distance divided by a change in time. Okay, so now let's think about this for a second. Here's an easy way to think about this. All right, I know there'll be some people who will say, oh my gosh, that line on the x-axis was too curvy, and I would have to try to agree with you. So you could move along this axis, you could move along this axis, but you know what? There's nothing that says that you didn't go this way, or that you went this way. Remember, this is your starting point. Or that you went this way. All right, or that you went that way. Okay, so if we let's take a look at this right here. If you're moving right here, and you normally would go from here to here, but you go from this starting point to this starting point, well, that was the same as what we were talking about here or here. Well, if you go from here to here, it could be, if you're going in the same direction, sort of. In math class, you've already identified this as being an angle, right? Some angle. And we tend to define that as what we call angle theta. All right, so there's angle theta. Well, then there was, well, this angle. There's another angle. We could mark that theta with a prime. And then we've got this one right here. All right, there's another one we've looked at. We could put a double prime on that one. You know, this one right here. We could just put an asterisk on it, just something, right? We could use a different letter. You know, we could put a different letter there. We could put an epsilon letter. We could put an alpha letter. It doesn't matter, but theta is typically used. So vector quantities involve direction. So it's not a matter of how fast, it's also a matter of what direction. So vector quantities are how fast and the direction. It's still the same equation. Velocity equals a change in distance over time. And we go distance over time, but we know that we spoke previously about displacement being delta x or delta y. So you will see these oftentimes written like delta y over delta t, or you might see delta x over delta t, because when we talk about displacement, we're talking about direction as well. So in this example that I have here, we would use our direction would be an angle. But we could just as easily talk about direction as being north, south, east, or west, or up, down, right, left. Forward, backwards, upward, downward, all of these are terminologies that we're going to be using to define the direction of our motion. And when we're talking about direction, that'll be a vector quantity. We'll call it velocity. Right? We will call it velocity when we are talking about direction. When we are not talking about direction, we will call it speed. It's the exact same equation for both, but the terminology we use to define it is just a little bit different. Right? So we've got stuff, we've talked about scalar versus vector quantities, difference between distance and displacement, very basic concepts, and then just linear motion means we're talking about something along a fixed axis. All right, and x and y are relative. Once you're moving in a direction, in a straight line direction, that is your x or that is your y. Doesn't matter which one you call it. For the most part, it's pretty much the same thing because it'll still be the same distance. You just need to keep all that in mind. All right, hope this helped. If you will just rewind, take a look at what you need, use the timestamps that are available for you to jump back and forth at different parts of the video, and definitely do your problem sets and ask questions if you've got any. Hope you enjoy this. Bye. And so there you have it. Defining linear motion. It's not that difficult of a concept, linear being a line, and so we're just taking a look at what's happening with an object, or we're going to find multiple objects, what's happening with it as acceleration might be occurring. The position is going to be changing and stuff like that. There is a difference between where the distance of something and its displacement. These are terms that in regular conversation we kind of use back and forth, meaning maybe similar things. But in physics, the words that we use have a specific meaning, which means that the calculation is going to change, and that's something you have to be aware of. So, hope this helped. It was good seeing you, and I'll see you on the next lesson. Bye.